Okay. Hi, everyone. So I figure I can go ahead and I already wrote up the sort of a warm up exercise for you guys. And yeah, like before, I think I'm going to have this sort of warm up thing. Will generally just be like a solo thing that you just kind of work out on your own on some, scratch paper or something. And then I'll just go over it and you can kind of like check to make sure you're on the right page and stuff like that. So I'll just give you guys the warm up now and we'll keep, probably some people will keep sort of filtering in as we do this. But we'll take, maybe, oh, well, plane's going over. We'll take like a little over 5 minutes. Let's say we'll resume at 5:15. So let's see. Here's the warm up. So yeah, we will resume at 5:15. We'll discuss it, and then of course I will, be happy to take questions, and I have some other exercises picked out for you guys to work on together. So hold on. Can you guys see the? I think it might be cut off. The last one here, VN. Can you see that?
Yeah, Vn is equal to -1 to the n plus 1 over n.
Oh, okay, okay, okay. Yeah, it's just my. I think my program is just glitching or something. All right.
Mhm.
Anyway, thanks. Okay, so let's go ahead and just go over this. So for the first part here, so we want a monotone subsequence from each of these sequences, right? So the first sequence here, it just like oscillates between a few different values, like you know, well, at n equals 1, you get you know 1/2, and so it's like 1/2, -1/2, 1, and then -1/2, 1/2, 1, and so on, right? So it only ever kind of goes between these like four different values. um, and like an easy way to make a monotone subsequence out of a sequence like that is just pick one of the like a subsequence that just repeats the same value over and over again. So like an easy way to do that here would be to take so let me like switch colors or something. So for Sn, take nk equals like 6k, for instance, right? Then you get the sequence that's just like cosine of 2k pi, so that's just 1. So it's just like 1 1 1 1 1 over and over again, right? So it's just constant, so that's monotone, right? For Tn, well, I mean, Tn is actually already monotone, so, right, it's decreasing. For Un, this is like an alternating thing. So if you just take n equals, or nk equals like 2k, oops, not Un equals. Take nk equals 2k, then you get like 1 over 4 to the k is your like decreasing sequence. For and that's the monotone subsequence. For Vn, this is again, I mean, you can just get rid of any like alternating phenomenon by just taking like either the even values or the odd values of n. So in this case, it's enough to take the even values of n. So you can take nk equals 2k again. Yep. Any questions about that? Okay. And yeah, definitely like feel free to use the hand raising feature. I have the little participant screen open, so I should be able to see that if you do it, hopefully. Okay, so now the set of subsequential limits. Okay, that's an interesting one. So for Sn, who wants to tell me what the set of subsequential limits is for Sn?
Is it 1 and -1?
Okay, those are subsequential limits, yeah, but there are actually more.
Also plus or minus half.
Yeah. Because so this sequence, it goes like 1/2, -1/2, -1, -1/2, 1/2, 1, and so on, right? So it repeats each of these four values like infinitely many times. So each one of the four values is actually a subsequential limit. So you get plus or minus 1/2 and plus or minus 1. So there are four subsequential limits for Sn. Tn, what's the set of subsequential limits for Tn?
It's just 0.
Yep, because Tn actually converges, right? So whenever you have a convergent sequence, the set of subsequential limits is just a singleton. It has only one element. For Un, it's the same thing, right? Un also converges to 0. And then for Vn, what about for Vn? So for Vn, the set of subsequential limits is plus or minus 1. Okay? Because they're basically, one the sort of odd numbered values here are tending towards -1, and the even numbered values are tending towards 1, right? And you know, if you form any, like if you take a subsequence here where you take like an infinite number of both the even and the odd terms, then the resulting sequence won't converge. So it can only be like one or the other, basically. It can only be plus or minus 1, right? Okay, any questions about these? Okay. So let's see. Now the lim_inf and lim_sup, right? Okay. So what are the lim_inf and lim_sup for Sn?
-1 and +1?
Yeah. So -1 and +1, right? Because, and now, so, okay, one way to think about it is just to like think about the sequence itself, right? And kind of think about the way, you know, the way we were thinking about it the other day, where you just kind of think about like, what are the biggest and smallest values the sequence tends to achieve? But now we can also think about it a little bit differently. Like once we've written down the set of subsequential limits, right? Then you can just read off the lim_inf and the lim_sup by just looking in there and seeing what are the biggest and smallest values, right? So for Tn, you'd get 0 and 0. For Un, you'd get 0 and 0. And for Vn, you'd get -1 and 1 again, okay? And then, so this one should have been pretty easy. So Sn diverges, just like, you know, it doesn't even diverge to plus or minus infinity. Tn goes to 0, Un goes to 0, and Vn just diverges. Okay, not to plus or minus infinity either. And then which are bounded, they're all bounded. So hopefully those last two were kind of gimmies. So that's the that was the warm up there. So for the next problem, I was kind of weighing a couple different possibilities, but I think I'm going to go with, hold on, send me the sequence. Right. Okay. I think I'm going to go with this one that I kind of just made up. So let's, I don't know, make a new thing here. Whoa. All right. So here's an exercise. Oops. So let S be the, actually, hold on. Okay, let's say, okay, T be the set of all numbers of the form n over 2 to the k, where n and k are in Z and n and k are greater than or equal to 0. Yeah. So this is all positive or non-negative integers divided by all like powers of 2, integer powers of 2. Yeah. And then take S equals T intersect 0, 1. Okay, so just all the numbers in here that are actually between 0 and 1 inclusive, right? Then the question is oops, there a sequence whose set of subsequential limits is S. Okay, so I think this is a pretty good little exercise here. I'm going to put you guys into groups now, and we'll work on it, and then yeah, we'll come back. Let's say 5:35 we can resume. So let me do this. Um,
Do we have to say what that sequence is, or just like say it exists?
if you have any way of arguing that it exists, then sure. You don't have to necessarily say what it is, but
Okay.
yeah, you should have some you shouldn't just like, shoot in the dark and be like, yeah, it exists, and leave it at that. All right, let's see. There we go. Okay, so I think this might be a little bit of a tricky problem, but so I'm curious, did anyone end up saying yes? And if so, can you tell me your sequence that you came up with? Yeah, Rahul?
I say yes because I guess not the rational number. That sequence with the rational numbers, I'm sure you could. There's a way of snaking around it to converge to.
Okay, so you're just saying basically sort of, you know, iterate through these values in a way that, you know, repeats each one like infinitely many times.
Yeah, but
Yeah,
then
like
is
you
it
could.
saying
Sorry, go ahead.
it's inclusive, or it has to be exactly S though, huh?
Yes,
The
exactly. Yes.
yeah,
Yeah.
that's a problem.
Uh-huh.
Yeah,
Yeah. Uh-huh.
so
Yeah.
that's
So
where I'm
I'm not
confused.
gonna actually, yeah, I'm not gonna get sort of bogged down in trying to describe a sequence that would do something like, you know, repeat each one of these numbers like infinitely many times or something, which you can do, by the way. I mean, that's possible to do. But the problem is that it's this, no sequence like this can exist just on the face of it because of the fact that, so the issue, so the answer is no. The issue is S is not closed. Okay. So the very last theorem from lecture 6 is that if you take any sequence and form the set of subsequential limits, that set has to be closed, which means, you know, meaning that if you form a sequence of you know, values from the set, right? So if you form a sequence whose terms are all members of this given set, then if that sequence converges, the limit of the sequence also has to be in here. So basically proving that this is not closed amounts to finding a sequence whose values are in S, but whose limit is not in S, okay? So did anyone actually do that? I'm curious. Okay. That's fine. I'll show you. I'll show you like how you can do this. So the first thing to do would be to pick a number that's not in the set, right? But that we expect to be able to get close to using numbers from the set, right? So I think the simplest example of that is just like 1/3, right? Like 1/3 is not in the set. So let's say 1/3 is not in S. But let's, you know, let's write down a sequence in S that approaches 1/3, right? If we do that, then we've shown that S is not closed. Okay, so here's a really easy way to describe a sequence like that. So we can take, let's say, Sn equals the maximum of the set of, or actually instead of Sn, I'll call it like Sk, just for consistency. So Sk will be the maximum of the set of n over 2 to the k, where 0 is less than or equal to n, less than or equal to 2 to the k, intersected with the interval, well, I don't know, whatever, 0, it doesn't matter, 0, 1/3, like that. Or even, actually, you can just make them closed on both sides. Yeah, that'll make it like more obvious that this set should have a maximum. Not that it isn't clear either way, right? So all I'm saying is like literally, you know, so like S1 would be like 1/2. Or no, what am I talking about? No, S1 would be 0. Sorry. But S2 would be, let's see, 1/4, right? So 1/4 is like the biggest multiple of 1/4 less than 1/3, right? So this would be like 1/4. And then S3 would be like 2/8, I guess, which is also 1/4. S4 would be like 3/16. S5 would be like 7, or no. Oh yeah, like 9, 10, 10/32. Sorry. Having a little trouble with the arithmetic. But anyway, do you guys get like how this works? So, so this kind of like manifestly, it's pretty clear that this is going to converge to 1/3, right? And so these are all from the set. And notice that, like, I repeated like 1/4 twice, and that's fine, right? It doesn't matter. But the limit here is 1/3, which is not in the set. So that's bad. Okay. Any questions?
For S4, how did you get 3/16?
Oh, I was just thinking, like, what's the biggest multiple of a 16th that's less than a third, right? Oh, sorry. It should be 5/16. Sorry, I'm totally like just spacing out. Yeah, 5/16. Sorry. Right.
And so it's the biggest, wait, what's the logic again? Like it's the biggest value that's less than 1/3?
Yeah, it's the biggest multiple of 1/2 to the fourth, right? So 4 is the index here. So you take 1/2 to the fourth, and then you say, what's the biggest multiple of that that's less than 1/3? Yeah.
I see. So that's, so the max applies to the whole thing, like the
Yeah,
whole
yeah. Sorry.
Oh, okay,
Yeah.
okay. All right.
Because the
Thanks so
max
much.
is a number, so you can't really intersect it with like a
Mhm.
set. But yeah.
Gotcha. Thank you.
Yep. Any other questions? Yeah, sorry, I don't know what happened with my brain there. Okay. So yeah, this is, I think, I actually think this is a really good question. But anyway, let's move on. I'll just make a new thing. Okay, so I had another one. Oh yeah. Yeah, let's do this one. I think this one's kind of fun. It's actually easier, I think, than the last one. So this is also from the book. So I'm going to draw a little picture for you guys. We have, oops, 1/2, 1/3, 1/4. And then we'll have 1, 1/2, 1/3, 1/4, 1/2. And I'll do one more row. So we'll form a sequence basically, okay, by traversing this diagram in a certain order. So we'll start at 1, then we'll go down this diagonal, right? Then we'll go, up this diagonal, and then we'll go down this diagonal, right? And so on, right? So you just like snake through this grid here. So yeah, by the way, so in the previous one, if you wanted to make a sequence that goes through all of the values of like n/2 to the k, what you first have to do is like, well, one way to do it would be to like describe a way to write out all of the values once in like a single sequence, and then repeat that sequence over and over again and just like snake through. So doing it once in like doing each value once in a single sequence is like a little bit tricky, because that's also itself like you can use like a snaking diagram for that one. So you can basically do like a double snake to get through all of those n/2 to the k values. Okay, anyway, so we have a sequence like this. So let's call that Sn. So this is Sn, right? The question is, oops. So find the set of subsequential limits of Sn, and B, find the lim inf and the lim sub. Okay. So let's let you guys, and we'll resume at like 5:53, let's say. Yeah. All right. So yeah, does anyone want to volunteer here to answer this question? Let's say part A. Okay, well, so, clearly, like, every number that actually shows up in this grid is a subsequential limit, right? Because each one gets hit infinitely many times, right? I mean, every single position in the entire grid ends up getting traversed. So, just like whatever indices correspond to like the first column, for instance, will give you all the terms that are just one. And so that subsequence will converge to one, right? And similarly, whatever indices are for the second column, right? So that'd be like 2, 5, 9, 12, or yeah, 12, I don't know. But yeah, you get what I mean. So there's a subsequence of all like 1/2 and stuff like that. So the set of subsequential limits clearly has, so S is like, has like 1, 1/2, 1/3, and so on, right? But that's not all, right? What else is missing?
0.
Yeah, exactly. Just the number 0. Yeah. And that's all, actually. That's everything. Because there are no other. So basically, one way of thinking about this is like the set of subsequential limits here, in this case at least. This is not true for like every sequence, but in this case, it's like you just take all the values that actually show up in the sequence as a set, and then take what we call the closure of that set, which is basically like you take this set of just the values in the sequence itself, and then add in any points that are like the limit of any sequence of these values, basically. So any point that these values like cluster around is the idea. That's like the vague idea of how you get the total like set. And then for the second one, right, it should be kind of clear that you just take the, so that was A. For B, the lim sup should be 1, and the lim inf is 0, right? Because those are the max and min of the set S. So yeah, in the last few minutes here, I think I'd just like to open it up to like general questions. If you have questions about anything so far. Yeah, Rahul?
In the last theorem that you put in the lecture, the 11.9, was that what the rigorous definition of closed is, or we haven't done that?
So it depends. That is a rigorous definition of what it means to be closed for sets of real numbers. Yeah, it's one rigorous definition.
Okay,
there are other definitions. Yeah, like so later on, it will, I think, once we get to section 13, it'll become preferable. And actually, now that I think about it, I'll post an announcement about this too, because I know there's a question on the homework that's like, show this set is closed, and I want to make sure everyone knows what that's actually asking about. But yeah, in the future, we might offer another definition, which is that a set is closed if the complement of that set is open. So yeah, okay. That's actually like the general definition. So in topology, like you can have topologies on sets that are like anything, basically. It doesn't have to be real numbers. It can be like there's all sorts of like crazy topologies out there. And for those topologies, like the way you define the open sets is literally just like by fiat. So you just say like, okay, this is an open set, this is an open set, this is an open set. You just specify the open sets that way. And then the closed sets are just like the complements of those open sets. So yeah, but for our purposes for now, this like the sequence thing is a perfectly good definition of being closed. Yeah.
Okay.
Good question. Audrey?
In the textbook, when it's discussing the Bolzano-Weierstrass theorem, it talks about how like some of the other theorems before that like work in the plane as well or don't, and I'm kind of confused about that.
Hold on. Let me go to where you're talking about. Right. Yeah. So, I mean, yeah, you don't really have to, this discussion right after the Bolzano-Weierstrass theorem in the book will make sense once we get to like section 13, basically. So like to really understand what they're saying there, like you can't understand what they're saying there like rigorously with what we've done so far, basically. But what they're saying is that like, so they say Cauchy sequences and bounded sequences make sense if you're thinking of sequences of points in the plane. And what they mean is that you can define a concept, okay? You can like define a concept of distance in the plane, and you can define what it means for a sequence to be bounded in the plane. And you can define the concept of a Cauchy sequence for sequence of points in the plane. And then like all of the things that we've proved about the definitions of like boundedness and like Cauchy and stuff like that will also be true for those definitions, basically. Okay. And like, if you want to know how you do that, so like in the plane, right, the distance between 2 points is like the square root of like the sum of the squares, right? So like the distance between like, well, I'll write it this way. Distance between like x1, x0, y0, and like x1, y1 is like the square root of like x1 minus x0 squared plus y1 minus y0 squared, right? Right, so like that's a concept of distance that you can define in the plane. And then what you can say is like, you know, a sequence of points in the plane is Cauchy if like, hold on. And then say like Sn, where now each Sn is like a pair of numbers, right? Sn is Cauchy if for all epsilon greater than 0, there exists n such that like the distance of like Sn and Sm is less than epsilon for all like n and m greater than n, right? So that would be like a definition of the concept of a Cauchy sequence for points in the plane, basically. Okay. And then, yeah, so like the Bolzano-Weierstrass theorem will be true in the sense that like, you know, if you say like a Cauchy sequence converges, for instance, which is true. I mean, you can also define convergence differently, but like if we were to say a convergence sequence is a Cauchy sequence or something, then like you could say the Bolzano-Weierstrass theorem, you can prove it for these kinds of sequences, and you can say like, you know, any bounded sequence in the plane, meaning any sequence that stays within like some like circle, you know, if you can find a big radius such that the sequence is bounded within that radius around the origin, then it has to have like a Cauchy subsequence or like a convergent subsequence. Yeah. Any other questions?
You know, when we define a part A, like the set, like one half, a third, and then we union it with 0, like could alternatively, could we just do 1 over n, where n is for all natural numbers?
Oh, yeah. That's,
Okay.
yeah. You know, it's just different notation, but yeah, you can say, I mean, that's kind of a better notation, actually. It's like sort of a bit more, you know, formal, but you could say like, yeah,
For
this
sure.
would be fine.
Thank you.
Yep. Other questions?
Oh, so like the 1 over n would include the 0 as well in it, right? So we don't have to do union of 0 anymore.
No, because you can't get, I mean, 0 does not occur as like when you divide 1 by n, like you'll never get 0 that way, right? So this set over here does not have 0 in it.
Oh, but like doesn't n go all the way to like infinity?
No, because n, this symbol here, this set does not have infinity in it.
Oh, okay, okay.
Yeah, this is just like the natural, it's just the natural numbers. So every element of this is just a positive integer.
I see.
Yep.
All right, thank you.
Yeah. Other questions? Yeah, same thing with like R. R does not contain the element infinity. Okay. So like if you want to talk about the set, like you can talk about the set R union like plus or minus infinity. Oops. That's like a different set from R itself, which just contains real numbers. And like Z also, you know, same thing. Yeah. Conventionally, plus and minus infinity are just like their own thing. Sometimes like in topology, actually this whole set are and well, actually not plus or minus infinity, but like are just with a single point at infinity is something that people talk about in topology as like the extended or like completed completed real numbers, but we don't talk about that in this class. So okay, so if there are no more questions, I think I'll end it here. Yeah. All right, see you guys tomorrow.
Thank you.
Thank you. See you tomorrow.
Yep.
Thank you.
Thank you.
Bye-bye.
Bye.